I'd like to start by thanking the organisers for this opportunity to come here and talk to you about some work I've been doing over the last little while with, in collaboration with David Burton from Lancaster University and a few other people. So we've heard a little bit about wave breaking over the last week, and I'll try to speak up a little bit, but yeah, let me know if there are any problems. Okay, yeah, so we've heard a bit about wave breaking over the last few days, but I'm going to try and give a slightly different perspective on it. So, as we know, strong longitudinal plasma waves can be used to accelerate particles, and by making those waves, those fields stronger, we should be able to get to higher accelerations. But there's a limit on how high the field can be made. As we drive the fields higher and higher, nonlinear effects will take over and eventually start to break the wave. Now, I'm not going to talk about the wave breaking process itself, but simply examine some of the wave breaking limits of what kind of electric field strengths can be propagated without breaking. And finally, I'll talk a little bit about how wave breaking limits can, or may be able to, reveal some new fundamental physics. Okay, so as we all know, if you send either an intense laser field or a particle beam into a plasma, it will generate an electrostatic wake moving at the speed of the drive up. So for relatively weak fields, it will be a sinusoidal wave oscillating at the plasma frequency, where zeta here is the wave phase and beta is the speed of the driver. So as we drive it harder and harder, there are two changes to this formula here. One will be that the field shape will become distorted. It will no longer be sinusoidal. And the other is that it will no longer be at the standard plasma frequency. The frequency will drop. And this will lead to a limit on both the strength of wake fields that can propagate and the maximum energy that a particle can gain by being accelerated in these fields. So how can we analyze these limits? Well, if we start with a cold plasma, that can be described by, well, the electrons in the plasma can be described by a density m and velocity v. We'll take the ions to be immobile over the timescales we're interested in. And n and v will evolve according to the continuity equation and the standard Lorentz force. So if you're not familiar with this in this form, this is just the acceleration, and this is E plus V cross B that you're familiar with. And if all the motion of the electrons is driven by the plasma wake, the solution to this equation will simply be that we can use V as the potential for the electromagnetic field. So this allows us to eliminate the electromagnetic field from Maxwell's equations. So Maxwell's equations themselves, if we assume that all the physical fields just depend on the wave phase, lead to two independent equations, one algebraic, which leads to the density as in terms of the energy and speed of the electrons, and a nonlinear oscillator equation is the other thing coming from Maxwell's equations. This is essentially an equation for the energy of the electrons, but not in the lab frame, but in the frame co-moving with the wave. So this is a nonlinear oscillator equation, and for small wake fields, where mu is just a little bit greater than 1, 1 is the point at which it's the equilibrium position of the oscillator. And if it's not oscillating very much, this gets back to simple harmonic motion oscillating at the plasma frequency. but you can see that for large mu, it becomes something quite different from that. So we can integrate that equation, and that will give us the constant of the motion. So this is essentially Hamiltonian, where you've got the kinetic energy term here and an effective potential. And we can see that because this whole thing has to be real, there is a minimum that that mu can come to. If it becomes smaller than 1 over gamma, this square root becomes, or the argument for the square root becomes negative. So we know that there are no solutions there, or no physically meaningful solutions. If we require the maximum possible amplitude oscillations, then we're going to want a turning point when mu equals 1 over gamma. So this term will vanish, and we get that orbits at the maximum oscillation have this value for the constant appearing here. And by noting that the electric field is given by the derivative of mu, and again that the maximum electric field will occur at the zero of at the equilibrium position of the oscillation, we get out the value for the maximum possible electric field supported by this equation. This was first found by Axion and Ploven on a very similar analysis to the one just shown, and a few years later by Dawson from a very different perspective, based on the motion of individual particles. Okay, so mu here is the energy in the rest frame, in the wave frame. So this is essentially the momentum in that frame. Yeah, so this is all standard stuff that's well known. The reason I wanted to go through it in some detail is to show that there are more controversial situations, and by following that well-established one, we can get some insight into those. So why might that not be enough? Well, mathematically it's sound, but it neglects some important physics. So if we look at the electric field close to wave breaking, we see there are these regions of almost constant gradient. But then there are these very sudden increases. And at these jumps, because of Gauss's law, we know that the density must be very high. So when the density is high, the pressure effects that we've neglected in the Lorentz force are going to become important. So we can't simply ignore them. Unfortunately, though, we're very far from thermal equilibrium, so it's not at all clear what the appropriate equation of state should be. So to try and get some insight into that, we can go back to the Vlasov equation. So when the momentum spread is significant, we can no longer describe the electrons by a single velocity field. Instead, we have to have a distribution that will satisfy this Vlasov equation, which is essentially just saying that every electron in the distribution is individually satisfying the Lorentz force, but collectively their motion will be slightly different. Now, the way this is usually used in this context, people don't tend to solve this equation itself, but use it to generate an equation of state to close the hierarchy of moment equations. That's often regarded as a simpler approach to solving the Vlasov equation. But in fact, this admits some very simple solutions. And let's have a look at those. So the simplest possible solution, you can see here, if f is constant, it will satisfy the equation. Unfortunately, this is no good because it gives an infinite density. But we can consider what's known as a Waterbag distribution, where f is constant in some region, and outside that interval is 0. And then the Vlasov equation is replaced or becomes an equation for the boundaries of this region, which turn out to satisfy the Lorentz force. Now, a distribution like this was first used by Coffey in this context to get wave-breaking limits for the non-relativistic plasma. And that's fairly uncontentious. But you might say, is this a very physical distribution? It looks a bit artificial. And this is true, but it should be noted that all solutions to the Vlasov equation that can be used in this context must have some irregularity. They can't be completely smooth. So this can be generalized to the to the relativistic case. And working directly with those equations, because the boundaries of the Waterbag are very close to the Lorentz force, the analysis is very similar to the cold case. We get this slightly more complicated nonlinear oscillator equation, where A here is essentially the square root of the temperature. And expanding this in A, to leading order, we get the cold fluid equation. And going beyond that, we get this correction to the maximum electric field. This is just in the limit that gamma tends to infinity. And you can see that for very large gamma, this will diverge logarithmically. This was found first by Getsulius and Murray, and then there's a very nice analysis by Rao showing that this is very reasonable. But it's not without controversy. There have been a number of alternatives posed in the literature. And one possible reason why you might not get a unique distribution is the restriction to one dimension. Now, simply by symmetry of the fields, we can argue that the space-time dependence should be one-dimensional. But it's quite artificial to say that the momentum spread, the temperature, should exist only in one dimension. So you can generalize the Waterbag distribution to three-dimensional velocity space, where it appears to become a lot more complicated. Instead of having 2 points as the boundary, we have a two-dimensional surface. Remember, this is in velocity space, so we've got one of these at every single point in space-time. Moreover, the points on this boundary are no longer required by the Vlasov equation to satisfy the Lorentz force, although that's essentially a gauge freedom to do with how we parameterize the surface at different times. So we can take it to satisfy the Lorentz equation. Now, we have to pose some structure for the boundary here. But even for a very simple case where at equilibrium they're spheroidal, we get a very rich structure. And it can be parameterized in that case simply by two constants, A, which represents the longitudinal temperature, and R is the transverse temperature. And again, the analysis is very similar, a bit more complicated because it involves an integral around the surface of the boundary. And we find that you get very different behavior depending on whether the longitudinal or the transverse temperature is dominant. So if the longitudinal temperature is dominant, then close to wave breaking, the Waterbag deforms like this, with points with no transverse velocity coming up to essentially the breaking point here. And that leads to a finite wave breaking limit as found in some of the literature using the warm fluid closure. On the other hand, if we take the transverse temperature to be much greater than the longitudinal, we get a very different structure where points around here where the electrons are not just moving forward in the wave direction, but also moving outwards, gain the most energy and come up to the wave breaking point. In that case, we get behavior that's much more like the the previous case, the 1D case. It's a bit surprising that the one where the longitudinal dependence is greatest is less like the purely 1D case. That's just a result of the doing these integrals around the boundary. Okay, so now I'm going to, having discussed the warm plasma case, I'm going to go back to cold plasmas, but have a look to see if we can uncover any new fundamental physics. I'll just very briefly go through this. So close to wave rating, we have extremely strong electrostatic fields. And it's expected that Maxwell's equations should be replaced by some nonlinear equations close to, or when you have ultra-high fields. Not necessarily saying the kind of fields that we get with wave breaking, but some of the reasons for these are the Euler-Heisenberg theory, as we heard in Anton's talk the other day. The electron-positron loops in QED can be interpreted as photon coupling, and that leads to nonlinearities. So it's theoretically very well established, but perhaps slightly out of reach experimentally. There's also the Born-Infeld theory, which has gained some popularity. It's initially introduced to avoid the self-energy divergences of the electron. It was also rediscovered from the string theory context. And essentially there, we just replace Maxwell's equations with these nonlinear equations where the Lagrangian L is some function of the Lorentz invariance of the electromagnetic field. And these effects typically serve to reduce the maximum possible electromagnetic field, and that's reflected, certainly in the Born-Infeld case, in the wave-breaking limits being reduced compared to the Maxwell equivalent. If you look at the energy gain, or the maximum possible energy gained in these fields, because these nonlinear effects also lead to a change in an increase in the wavelength, the plasma wavelength, we end up with the same maximum possible energy gain in Maxwell's, all these nonlinear theories as we do in the ordinary Maxwell theory. And just very briefly, there are many theories beyond the standard model that introduce very light scalar particles which have this unusual coupling to the electromagnetic field. These also can modify Maxwell's equations. But we've got fairly tight limits on parameters in this coming from astrophysical observations. Now, in the laboratory, these are not going to be observable. But it has been suggested that wakefield acceleration could be responsible for, in astrophysical context, could be responsible for ultra-high energy cosmic rays from wakefield acceleration around a neutron star. And you have extremely strong magnetic fields around a neutron star, with E being over 10 to the 8 Tesla, even up to 10 to the 11. And you find there that the maximum energy gain, if axions do exist, gets reduced by this factor here. Now, this depends quite sensitively on these unknown axion parameters, but using the limits that are available in from the observations, it can substantially reduce this. If you stick to the limits, it's 90% reduction, but it depends very sensitively, so it's unlikely that we can actually use this to observe, to put a definite restriction on axion properties. Okay, and as I've overrun a bit, I will just put my summary up there and leave it at that. Thank you.
Okay, so question? Yes, Bob.
Is it possible to use the axions to modulate the plasma around about the
Yes, so that's what would happen here. Sorry, I rushed through this a bit, but essentially you have a full coupling of the electrons, the axion, and the electromagnetic field. Although the electrons and the axion don't directly interact, when these effects are strong, they'll interact via the electromagnetic field, so you will get substantial changes to the plasma as a result of it. Okay, so using an axion driver, that's something we haven't considered. So in this analysis, we've just said that the axion is generated by the plasma and the magnetic fields of the neutron. But yeah, that's something else you could consider.
I have one comment and one question. First thing is about the cold plasma Kaiser-Polovian limit. The answer is that actually there is no limit in reality. I mean, a relativistic wave will always break, whatever be the amplitude, through phase mixing effects. And
I think there are ambiguities with what these calculations are actually telling us. In a sense, these are maximum possible wave-breaking limits, but it's not saying that you can't, if you perturb the wave about these standard electrostatic waves, they could break at a lower field. So you're not guaranteed to get up to these.
Right. And the second question is that in the 3D Waterbag model case, the wake field is also multidimensional, right?
So the wake field is also?
The wake field, that is also multidimensional?
No, in what we've done here, we were just, it's only in the velocity space that we include the transverse effect. So
that's the distribution, right?
Yeah, but only in the velocity part of that. In terms of the spatial components, the wake field is still just one-dimensional.
Wake field is still one-dimensional.
Yeah, so
you would expect the wake field to curve, right? If the temperatures are different in different directions, right?
Well, you still have complete symmetry in all the initial conditions for the transverse directions. Essentially, you've got a flow of particles, but your conditions are still the same at all transverse points. So there's no sort of position for which it could curve around. And certainly there are 3D effects that should be taken into consideration.
Okay. Thanks.
Okay, thank you very much. So we'd like to move on to the next talk.